Okay, we need to look at more adiabatic changes and the carnot cycle, which is the most efficient thermodynamic cycle. So you know that an adiabatic change is a fast process. There is no time for the thermal energy to be transferred, so Q is equal to 0. So if we use this formula, Q is equal to delta U plus W. In the case of an expansion, you know that Q is equal to 0, and you know that it's doing work, which is positive, so therefore delta U must be negative. So T is not constant, so it means that the temperature will sink down very quickly, a bit like producing dry ice. Now often we change P and V, and we use them in PV is equal to nRT, and in this case T is constant, so PV is equal to constant. However, in an adiabatic change we can't really use this formula because the temperature is changing, so we have to adapt it slightly. So for an adiabatic change, T is not constant, so we use this formula instead. So this is a formula that might be needed, but it only works with an adiabatic change. PV to the 5/3 is constant. So here we have alternating adiabats with isotherms. The one on the top is an isotherm. P is inversely proportional to V, and that's when there's a Q going into the system. There's thermal energy going into the system. But the next part is an adiabat. This is an adiabatic expansion, and there's no Q is equal to 0. Then there's no transfer of thermal energy into the system. This is also a line of constant entropy, because you know that the entropy depends on the change of Q. And since there is no change of Q, there is no entropy change. The efficiency of a heat engine. Now, this is the efficiency equation, useful work divided by input energy. So let's do a heat engine. We have a hot reservoir, a cold reservoir, the heat engine now. So thermal energy comes in from the hot reservoir, produces work, and some energy is ejected. So if we say the input energy is QH, that turns into QC plus W. So the useful work is W divided by QH, but we know that W must be QH divided by, QH minus QC. Now, if we have this formula here, and we divide QH and QC by QH, we end up with 1 minus QC over QH. So the efficiency formula can be used in this form. Now we're going to get onto the Carnot cycle. The Carnot cycle is a cyclical thermodynamic process which has the maximum possible efficiency, and it alternates isotherms and adiabats, as we've just seen. So this is the Carnot cycle. So we have for going from 1 to 2, that's along an isotherm. From 2 to 3, that's along an adiabat, and so on. So this is an isotherm, and this is an adiabat. So the efficiency is the useful work divided by the input energy, which we also know is equal to this. Now, in a Carnot cycle, we can actually represent that not in terms of the thermal energy that's transferred, but simply as the temperature of the hot reservoir and the temperature of the cooled reservoir, the cooled sink, as it were. So the Carnot cycle, the efficiency is 1 minus Tc over Th. You might want to think, how can we get the Carnot cycle to be as efficient as possible? What's the maximum value we can get, and how will that be? And the second question is, how can the efficiency of the Carnot cycle be 0? In other words, 0 efficiency.